Welcome to Study Loop.
So this question starts by asking to find the wavelength of a photon at the max absorbance of TDSA. So if you look at the figure given, the max absorbance of TDSA is equal to lambda equals 355 nanometers. So this is the max absorbance of TDSA. And so we want to convert that into meters by just multiplying by 10 to the minus ninth. And so now our wavelength is in meters. And we can find the energy of a photon with the equation E equals hc over wavelength. And so h is Planck's constant, 6.626 times 10 to the minus 34th. C is the speed of light, 2.99 times 10 to the 8th. And the wavelength is what we just had above, which is 335 times 10 to the minus ninth. So when we solve this, we get that the energy of a photon at max absorbance for TDSA is 10 to the minus, or 5.91 times 10 to the minus 19th joules. And so moving on to letter B, this time we want to find the energy of a photon at the max absorbance of 2 EHMC, which if you look at the table, the max absorbance is wavelength equals 310 nanometers. So again, we want to convert that to meters by just multiplying by 10 to the minus ninth. And then we use the same equation as before, E equals hc over lambda. So h is Planck's constant, 6.626 times 10 to the minus 34th. C is the speed of light, 2.99 times 10 to the 8th. And the wavelength we just found to be 310 times 10 to the minus ninth meters. And so when we solve this, we get that the energy of a photon here is 6.391 times 10 to the minus 19th joules. And so letter C just asks which of these have a higher energy, and that is 2 EHMC has the higher energy. As we calculated before, you can look back at A and B and see that it has the higher energy. Now letter D asks, why would sunscreen contain both of these chemicals? And the reason for that is to absorb multiple wavelengths of light. So instead of just absorbing light at 310 nanometers with just 2 EHMC, or absorbing light at 335 nanometers like TDSA, by having both these chemicals, you can absorb light at both of those wavelengths and thus allow for more productive sunscreen. And so the final letter E wants us to find the joules per hour absorbed by someone's skin. And so it gives us that you assume it absorbs half of the 2.066 or the 3.066 UV photons per meter squared second. And so we just divide that by 2 to be 1.533 times 10 to the 22nd. And that's UV photons per meter squared second. And so now we want to find the energy of a single photon, which of course is E equals hc over lambda. And so h is Planck's constant, 6.626 times 10 to the minus 34th. C is the speed of light, 2.99 times 10 to the 8th. And then it says to assume the wavelength is 330 nanometers. So we multiply that by 10 to the minus ninth to get the answer in meters. And thus we find the energy of a single photon is 6.00 times 10 to the minus 19th. And that's joules per photon. And these are also UV photons, as with the 1.533 times 10 to the 22nd. So now we just want to do some dimensional analysis to get the answer. So 6.00 times 10 to the minus 19th joules per photon. We multiply that by the given answer, the 1.533 times 10 to the 22nd, and that's photons over meters squared seconds. And so now our photons cancel. And so now we want to move into converting this seconds into hours, as the question is asking for the amount of joules per hour. So, of course, 60 seconds in 1 minute, 60 minutes in 1 hour. And so now minutes cancel, seconds cancel, and we also have to multiply by the area of exposed skin, which is 0.42 meters squared. And so now meters squared cancel, and we end up with joules per hour. So when we do this math, the answer is 1.39 times 10 to the 7th joules of energy are absorbed per hour. And that is the final answer for letter E.